So let's get back. So we have just said that decision trees do not really care about continuous or discrete values. That's fine. At least from a conceptual perspective, obviously continuous values may require more computation time. That's almost always true. But they care about missing values. Okay, so missing values can be a problem because we don't know basically how to calculate splits. Okay, we split an attribute based on the admissible values, but for some rows in our database, we don't have any values available. Okay, so the question is how to count in the Gini rule, in the information gain rule, how to count the missing values. So I would argue that in general, if you can afford it, simply remove any kind of data point that has missing values, if you can afford. We already have had this discussion. If you can afford basically means if you do not lose too much data. Okay, if I have a database with 10,000 lines and by removing any lines with any missing value, I get with hundreds of lines, probably I cannot afford that. But if you can, just remove the missing values. Obviously, this is not always possible, so you need to make some choice. So, obviously, you can avoid doing these things if you fill in missing values. Okay, we already had this discussion too. You can decide to fill in missing values with any given fixed value, which is almost always a bad idea, or depending on data distribution. So if I have for a column, for a feature, if I have missing values, and hopefully they are not the vast majority of values, I can try to fill these missing values with any given filling criteria that is based on the distribution of the actual values for the column. Okay, so for instance, simply, I don't know, compute a Gaussian probabilistic distribution with mean and variance of the mean and variance of the values that you have, and to fill the missing values, draw a sample from this distribution. That could be reasonable because you are not altering at least the data distribution. Okay. So, first answer to this question are first drop the missing values if you can, or replace them somehow if you can, if there is a good criteria. Otherwise, basically the core of the issue is where to put branches in which we have missing values. Okay, we have a data point. I have a missing values for the attribute that I want to use as a split. So in which branch do I put it? The simplest answer is follow the majority. So I put the example in the branch that has the majority of examples. Or we can try to weight all branches. So do a probabilistic choice, and the probability is based on the relative proportion of each of the of the branches. That could be another answer. But usually this kind of stuff, as we have seen many times, doesn't have really an a priori good choice. You have to make some tries and see what happens. So summing up, why decision trees are basically cool, are basically a good choice in the vast majority of situations, because they are simple. Okay, they do not require any implementation complexity or some sort of complex reasoning about how to use them. They are easily to be interpreted, okay, which goes in favor of explainability, which is a topic in AI that has lots of attention nowadays. They are called, in fact, machine learning models that usually are split into white box or black box. Okay, so white box or glass box, as here, are machine learning approaches that you can easily look into. Okay, that you can easily understand what's going on. The classical example of black boxes are neural networks, because it is not so easy to check what's going on. If you look inside a neural network, the only thing you see are random numbers between neurons. That's what you see basically. Keep in mind that they have some drawback. They are prone to overfitting, so you must, from the very beginning, start thinking about minimizing the chance of overfitting. And this is a consequence in reality of overfitting, exactly because they are learning a model that is by its very nature tailored to the training data. Even small variations in the training data can lead to quite different trees. Okay, that's the nature of the whole idea. You can do basically anything about it. Something you can do. It is quite rare nowadays to see decision trees applied as we have seen up to now. Usually they are applied in a way that is called random forest, which is it may appear as a dumb idea, but it works. So if it works, it's not dumb. Exactly because of this, especially because of these reasons, that even the slightest variation to the training dataset can lead to quite different trees. The idea is, do not train one tree, which is usually computationally quite effective. Train a bunch of trees. So create a forest. That's why it's called a random forest. Many different decision trees, each learned usually on a different subset of the attributes. So when I do my train validation test split, for each tree I want to learn, let's say I want to learn 5 trees. They can also, all 5 trees can also imply the same learning algorithm, okay, it's fine. All of the trees are learned using C4.5, fine. But I learn 5 of them, and for each 5, the train validation test split that I use is different. For instance, I shuffle the data. I shuffle the rows in the dataset. And then you can simply average the prediction or use a scheme like majority voting. I have 5 trees. 2 trees predict one class, 3 predict another class. I predict the majority of the classes. Fine, okay? This method of creating a random forest is actually belongs to a family of methods which are called ensemble methods, because they use a collective of decision trees. They use multiple models. The random forest is the name of the decision trees ensemble method, but you can use ensemble methods for any other machine learning model, basically. We will see support vector machines, neural network. Obviously, you can iterate this reasoning. I train more neural networks. I train more support vector machines. That's an ensemble method. So this is a simple example. I have my dataset. I train 3 different trees. I can train them with the very same method. I don't care. I can only change simply the data distribution, so the training subset of data that I'm using for each tree. And then I simply, to decide which prediction to output, I can simply adopt majority voting, okay? Obviously, for instance, if you have a binary classification problem, prefer an odd number of trees so you don't have ties. If you have a multi-class, also try to choose a number of trees that can't give you ties. Otherwise, you need a criteria to resolve ties. That's a very easy idea, okay? This leads us to the general, let's say, approach of ensemble methods, as we said. And when you are trying to compose together the output of different machine learning models, this applies beyond the decision trees. Usually you have 3 ways of composing the output of multiple models: bagging, boosting, and stacking. Bagging is basically what we exemplified up to now. You train a few classifiers. Obviously, they don't need to be weak, but usually you do this when your classifier is not really good. So you train a bit of models, homogeneous in the sense that they are the same model. They are decision tree, they are subvector machine, whatever. You make them learning in parallel, so you don't need to wait for one model to learn, okay? You can train them in parallel on multiple CPUs, on multiple GPUs. We don't care actually about parallel or distributed learning because it is more or less a technicality. And somehow you aggregate the results, like we said, for instance, with majority voting. In boosting instead, you do a slightly different thing. You put the models not in parallel but in sequence. You train a first decision tree, then you try to retrain it somehow. Then you retrain it somehow. Then you retrain it somehow. Okay, and now you need to define a strategy to combine these results. Okay, so for instance, you can have a first dataset. Let's try. One method is called gradient boosting, which is a sort of incremental way of improving a model. Let's see how a boosting ensemble method may work. You have your first dataset, you train a tree, okay, and then you test the tree. Then what you do, you train a second tree, for instance, only on a subset of the dataset, or on the dataset, original dataset, augmented with the output from the first decision tree, okay? And you can iterate this, flagging correct and wrong predictions, okay, as you go, and then hopefully your last tree will be the most accurate. Because at each step, you decide how many. Usually you measure some form of performance like accuracy or precision. In each iteration, you replace your dataset with a subset containing wrong prediction because you want to improve on the wrong predictions. Beware that one possibility of this is that we already mentioned it, so it should be quite easy to see the potential issue here. Actually, here you are a bit of worsening overfitting because you are training more and more on a narrow dataset specific to some points. So beware that gradient boosting can overfit easily. Stacking is another technique. Again, you can learn in parallel many models, and then you can combine them, but not simply averaging output to stuff like that, but you need another model. Okay, so this is one thing that we will not enter into the detail, but you can train a model to actually learn how to compose the model that you learn. This is, let's say, a complication that we don't need. As usual, as I anticipated, for every kind of technique we see, we also see a practical example. Again, the library of choice is scikit-learn, and we have this wine dataset that you can check in the code repo. The dataset regards chemical properties of wine, okay, and obviously your interest is to try to predict the quality, I think, of wine. This is the list of attributes. For instance, you have the quantity of alcohol, different properties, alkalinity, if there are phenols, the color intensity, and stuff that I have no idea what it is. And then we can see what happens when we try to apply what we learned in a practical example. So, if we go into our code repository, we have this decision tree, and we have our usual, let's say, steps. So for instance, we want to load the dataset, okay. We want the dataset is not here actually, yes, because it is one of the classic example datasets, so it's already included in the scikit-learn library for free. So as we did with the KNN example, which was about, I don't remember, breast cancer, I think. We didn't have the explicit dataset because it was already included. We load the dataset and we immediately split the dataset into the features and the prediction target. Okay, we want to keep them separate. Then we do the usual splitting, fixed proportions. 20% of the dataset is used for testing. Okay. And we do the three subsets that we already did for KNN. First of all, we split the whole data set in testing, 20%, and training and validation, 80%. And then we further split train and validation, again, 70-30 this time. This is the same splits that we did, I think, in the KNN example. And then, as we are learning, actually, it is very easy to create a decision tree with a library, specifically with scikit-learn. We simply instantiate a decision tree classifier, and we have the same method that we had for KNN. Exactly the same. That's the strength of the library. Whatever model you are using, KNN wasn't even learning, if you remember, you have the exact same interface, okay, the exact same methods, more or less. So you create the classifier and you fit the classifier to your data. It means that this fit procedure may last a lot of time. It depends on your dataset. Here is where training happens. Okay, so if you have a dataset with hundreds of attributes and thousands or millions of lines, this single method call, function call, may take a while, okay? Because that's the method that hides all the learning machinery. So what's going on here? Well, for instance, for a decision tree employing C4.5, what's going on here is trying to do all the splits. So take any attribute, compute the information gain ratio, do this for all attributes, choose the one maximizing the information gain ratio, do the first step on the first split on that attribute, then recur on the leaves. Go on until either stopping criteria is met. You find a perfectly pure leaves, you have a few examples, or more often than not, if you have a complex real-world dataset, some time limit is reached. Okay, I have a budget for training. I can train the model for, I don't know, 1 week, and that's my limit. I don't care about impurity, fewer number of examples. I have a time budget. But all of this magic happens here. After you have called fit, your decision tree is created. So you can predict on test. Here we are not using cross-fold validation. No, this is a simplified process. So if you notice, we are training on the train validation set. We are not only training in training set. And so we have a first classification report, for instance. And one nice additional benefit that the scikit-learn gives us is that you can actually visualize the tree in a textual way, okay? And this is to make sure that you have the correct feature names. Or you can also export the model graphically. You have a few alternatives. I put in here 2. This is one alternative that is, let's say, native to scikit-learn with this plot tree method on the tree object. Again, you load the feature names, you give the model, and then you show. Or you can use another library which is called GraphViz, which is very famous. So you can find mention of it, and more or less is the same. You simply need to. In this case, we are also saving the feed, the created figure on a file. Okay, so let's stop here before the random forest. Let's try to see what happens. Here. So as I said, you can simply run the examples by executing the Python script. So this is decision trees. If nothing was wrong. Okay, so let's check what happened. The program is still waiting, but let's check what happened here. So this is our first classification report. Again, we are not really, the examples are not meant to optimize performance, okay? So we don't really care about the performance. For instance, here, we should have done what we learned with KNN. We should have done training in training, then cross-fold validation using validation, and then testing afterwards. Here we are a bit shortening the pipeline. This is our usual classification report. We didn't plot the confusion matrix, but we could. And as you can see, we have this kind of, we have three classes here, so three target classes, a multi-classification problem, not a binary classification problem. So you have all the metrics for all the classes, as we said. You have the precision of all the classes, which is more or less the same, quite nice. We have the recall, which is not so good on the first class. I don't remember actually what the three classes are. And we have the F1 score, which again follows a sort of combination. Your overall accuracy is, well, not so bad. And after this, you have actually a textual representation of the tree. Okay? This is obviously not as easy to navigate as the graphical one that we will see in a minute, but it is convenient if you want to log it to a file, for instance. The first attribute, the first column in your dataset that you are splitting on is the attribute proline. That's it. And you split it in whether this proline attribute has a value lesser than or equal than 76 tenths or above. Okay? That's it. That's what your decision tree is telling you. Then the second attribute, in the case proline is below the threshold, is this kind of random gibberish diluted wines. Below 2.11, above 2.11. Keep in mind that it is not necessarily the case that this same attribute will be the next attribute in the other branch. It may be, but it is not necessary. And in fact, it changes. In that part, in that subtree, the second best attribute to do the split is color intensity. Can be. Okay, nice, but reading text is painful. You can have a graphical representation. I don't know why this doesn't work, but you should be able to zoom. Anyway, here what we have. Let's try if I can zoom in some other way, but I don't think so. No. Why the zoom doesn't work? Anyway, in the next representation, I think we actually can. But if we could zoom in, here we will have the same data that we had in the textual representation. So the attribute and the values for the split on the branches. But also, in each box, in each node, we will have additional information, like, for instance, the Gini index, the value of the Gini index, the value of the information gain ratios, this kind of stuff. And you can obviously save the figure if you want, do whatever. So let's try to go ahead. This was the first visualization. This was the first graph. The second graph, we didn't show it, but we saved it as a PDF. That's actually the same graph, okay, the same decision tree. It is only a different libraries to show. And as you can see, you have basically what I told you. In each node, you have the split, the kind of split. It depends on the visualization. Sometimes you have this rule in the branch, in the branches. Sometimes you have in the node. So you go in this branch if it is true that proline is the value of the attribute proline is below that. Then you have the Gini value, the number of samples, and the distribution of values between the samples. So you have some additional information. And again, you can find all the rules, basically, okay? These are pure nodes. In this case, probably the stopping criterion, the default stopping criterion is go on until you find pure nodes. Any question about this? This could be quite, this should be quite intuitive, okay, to check. For instance, what is one decision rule in this tree? One, by chance, is if the proline field value is below 760 and the diluted wines is above 2.11 and the flavonoids is below blah blah blah, I compute this prediction. Okay, I assign this label. That's a rule. Some other observations that I can do. What we can do based on what we learned from the slides. The first two splits, the first one and the second one in the true branch, are not extremely meaningful because the Gini index is more or less around 0.5. So they are not really meaningful. Okay. Remember that for the Gini index, we want to minimize the Gini index. So here we have better splits. Okay. That's one thing I could say. Another thing I could say is, if training this model didn't take a few seconds but lots of hours, let's assume, well, probably a good criteria for stopping could be, for instance, the number of samples. In this node, there are only 3 samples. They are very few samples out of the original 142. These are small data sets, okay, to keep the training time reasonable. Here we have a few samples, here we have a few samples, here we have a few samples. Okay, so in fact, not because of the sample, but because of the Gini index, but this is not split anymore, this is not split anymore. If here, for instance, we have a lot of samples here, if the Gini index wouldn't be 0, probably we would have done another split because we have a lot of samples here. Here instead, even if the sample is 1, so here it couldn't happen, but here, for instance, even if the Gini index wouldn't be 0, probably it is not worth to do any more splits. We only have 3 examples. Maybe we can tolerate some issue. Also because, keep in mind that we don't want to overfit. When you have leaves, lots of leaves with few samples, that's a good indication that your model overfit. Obviously, in a very simple data set, overfitting may not be a problem, but in general, it could be. Then in the same example, I also put some examples of ensemble methods. So here, for instance, we are training, our model is not a single decision tree, an individual, a singleton model, but a random forest. As you can see, the training is the same, prediction is the same. We want a classification report, and we got the random forest classification report, and as you can easily see, it already improved. We used some default parameters. You can imagine that here there are some parameters. For instance, even the number of trees I want to generate. I didn't care. I don't know how many they are, 5, 10, I have no idea. We used some default parameter, but obviously, if you do some project on this, you can check the documentation and see what kind of parameters you can play with. And then we tried also gradient boosting. Again, no parameters, so we don't really know what's going on, but if you remember, gradient boosting is an ensemble technique that uses not bagging, like random forest, but boosting, gradient boosting. So training not in parallel and then averaging predictions, but sequentially different decision trees by trying to improve on the error rate. In this case, the gradient boosting improved over the individual decision tree, but the random forest is still superior. And that's it, basically. Okay? Obviously, you can have fun playing with parameters, see what happened, playing with features, for instance. We basically didn't do any pre-processing here. We will see in some future examples also some pre-processing. Here we didn't do any pre-processing. Maybe instead it is good to do some pre-processing because some of the features are irrelevant, okay, are noisy, whatever. And that in the slide, more or less, you should have the same example, but the slides are just a pointer to the code base, okay? So take the code base as a reference, because if I find errors or improvement, I may forget to update the slides. I shouldn't, but I may forget to update the slides. Okay, so now we have seen our first machine learning method, because remember that KNN wasn't actually learning anything. It was a sort of baseline, a first example of prediction model, very basic prediction model, naive prediction model. Then we have decision trees, and then we look at linear classifiers. What are linear classifiers? Linear classifiers are simply prediction models that try to predict the target variable by using a linear combination of the input features, as the name suggests. So what you are trying to learn is actually a linear function that helps you discriminate the target classes. Okay? There can be many techniques to create a linear classifier. Even a neural network can create a linear classifier. Okay, so keep in mind this is a family classifier, as in decision tree. One thing is to talk about decision trees as a model of how to take decisions. One other thing is to talk about C4.5, which is a specific algorithms for learning a decision tree. Here is the same. Linear classifiers are another family of classifiers. There are many ways to actually learn a linear classifier. Again, this is quite simple, like decision trees. The very first algorithm you should try are these, basically. And exactly because it's simple, if you have a very large data set or the task is very complex, it can be the only available option. And for instance, talking about neural networks, one of the very simplest form of linear classifier is called the perceptron, which is actually a neural network with a single neuron. Okay, this is more of a toy example to give you a bit of a history, because this has strong limitations. We will see in a minute. So this linear classifier aims to learn a function which is simple, a sine function, okay? So based on the input data, learn some parameters that enables me to discriminate between a positive example and a negative example. It has a biological expiration, as the name suggests. In the brain, actually, neurons work more or less this way, so they get inputs from synapses. When the input is strong enough to surpass a given threshold, the neuron fires another signal on the output synapses. That's how, in a very simplified way, neurons in the brain work. And this was an inspiration for Rosenblatt, actually, the guy that actually, maybe we have some dates. Ah, yeah. So I was about to say 70 years ago, yeah, more or less, had the inspiration, okay? How can we represent this kind of function that we designed? This way. We have our input data set. Each data sample is weighted, and this is actually the parameters that are under learning. You somehow aggregate all the input, and usually this somehow is a summation. If the summation of all these weighted inputs is above a certain threshold, you give an output. Okay? So, in this function, what we name it beta are actually these weights. Okay, nice. This is more or less the architecture of our model, okay? The shape of the function we want to learn. How do we actually train the beta parameters? Okay, these are parameters that we are not giving to the algorithm. We expect them as output to be learned. How? We define a loss function. We will see the loss function again in the future, to be minimized. What is a loss function? But usually is the error, the classification error. Okay. Remember that we are still in the realm of supervised learning. So during training, you know if you did an error or not. You can measure the error, unlike unsupervised training or reinforcement learning. Okay? So this loss function, we already had a few examples: the mean squared error, the root mean squared error, the what was the other one? The mean absolute error, I think. These are all loss functions. Choose whatever you want. You can even try to compare different loss functions, okay? A loss function can be whatever, but usually is a function that you want to minimize and that somehow measures how correct your predictions are. How correct your function approximation is. So, for instance, the loss function is, in the case of the perceptron, the loss function is extremely simple. Just take the sign. If there are different signs between the predicted outcome and the actual outcome, well, that's a wrong classification. So it is a very simple loss function. Okay, how do we minimize the error? With gradient descent. Have you heard before about gradient descent? Maybe also in our overview slides, we mentioned gradient descent. This is the gradient of the error function. Okay, I did a mistake, no, in my prediction. Okay, how can I correct the mistake? Well, look at your input data, your x1, x2, x3, x4, xn, and do the gradient is actually the partial derivatives with respect to all these features, and so try to understand in which direction you should adjust your prediction. This is in the general case. In the case of the perceptron, it's very easy because you only have two cases. Either the sign was correct, either the sign was wrong. So if I got a minus sign and I should have got a plus sign, simply steer your prediction towards the plus sign. And so you adjust these weights by considering the gradient of this error function with respect to the parameters. Okay? So I did an error. Now I calculate the gradient, the partial derivatives of all the features, and then I adjust my weights. In doing so, and we will go a bit deeper into gradient descent when speaking about neural networks. While doing so, the only parameter we have, which is actually what we call an hyperparameter, so something that actually we should give the algorithms, is the learning rate. The learning rate basically dictates how strong the correction should be. Okay? How much do I change beta in the next iteration? I change beta of, I don't know, 10 in magnitude, or do I change beta by 1 or by 0.1? Okay, so this is called the learning rate because usually a larger learning rate means you are learning fast. Okay, so for every error you make, you try to greatly modify your weights because you want to learn fast. You want to converge to the solution faster. There is a catch. You are learning faster. This does not mean that you are learning the right thing. Okay? For instance, if your solution space has some sort of local optima, it means that you are converging faster to one of these optima. It doesn't tell you anything about is this the global optima or a local optima. I don't know. So you are simply learning faster. Usually, a higher learning rate also gives you instability of learning. You can find your loss function that goes up and down, up and down, up and down at every iteration. Usually, the learning rate is kept, in fact, as low as possible. What does it mean as low as possible? As low as you can afford. Because as we said, a higher learning rate means faster learning. So a lower learning rate means slower learning. It takes time to learn. Time means computational time. Okay? So usually you try to keep the learning rate as low as possible depending on what you can afford. I can afford 1 week of training time. Okay, I set the lower learning rate that I can. I can afford 1 day of training time. I must increase my learning. Exactly what is written here. We will see, I think not here, but expanding on this first simple case of perceptron in neural network, we will see that there are algorithms that adapt the learning rate during training. Somebody noticed that having a fixed learning rate is not a good idea. Gradient descent is it's actually the standard de facto to do this minimization of loss function. It has a, let's say, mixed feelings theoretical guarantee. You are guaranteed to reach a local minimum, which is better than nothing, but it is not the global minimum. Okay, so we will see again that there are ways to try to escape local minimum. But for now, we only care about the structure of the perceptron. It is a simple linear combination of features. We try to learn the weights of the features to decide basically whether to say, okay, this is a positive example, or no, this is a negative example because the threshold didn't get achieved. And we only care about this concept, the concept of a loss function to measure the error, and the technique of doing gradient descent to adjust the parameters, trying to minimize the error. You can do gradient descents basically in two ways. Actually, there is a third way, which is a combination of both. You can do gradient descent in batch or what is called stochastic for some reason. Usually, as we actually depicted here, you need all of your data points. Okay? You feed all of your data points to the network, you try to do the predictions of all the data points, and then you propagate back, you do the gradient descent to try to adjust the weights. This can be computationally very expensive. And so this is called the batch gradient descent. Okay? So all of the training samples and the gradient that tells you how to modify your learning parameters is computed on all the examples. This is computationally expensive, so usually what you do is stochastic gradient descent, which means that ideally, theoretically, after each example, I do this error computation and gradient descent and adjustment of parameters. Stochastic descent actually gives you faster training. If you keep the same learning rate, stochastic descent is faster, obviously because you are feeding one example at a time, not the whole data set, so it is computationally faster. This can also help to avoid the local minima. I anticipate usually what you do in practice is an hybrid. You do what is called mini batch. Do not feed all the data set at once, but do not feed one example. Feed some number of examples. I don't know, I have a data set with 1,000 of rows. I feed 30 rows at a time, 100 rows at a time, 10 rows at a time. This is a mini batch, okay? Empirically, this is the technique that usually works best. So the perceptron may be nice because it's simple, but it has a very big drawback. The perceptron, by its very definition, it is theoretically proven that can only classify, sorry, I don't know what I did. Okay, I can only classify linearly separable examples. I don't know if you heard about this, but in the whole AI field, there have been multiple so-called AI winters. I don't know if it's the first time that you hear this term, but basically an AI winter occurs every time that disillusion about any given AI techniques takes over. Okay? So, for instance, it may happen in AI winter if we figure out that, I don't know, large language models are not really so good. So actually, one first AI winter happened when, I think it was McCulloch and Pitts, but I'm not sure. Anyway, two researchers demonstrated that the perceptron was only capable of doing linear separations. Okay? So for instance, a simple thing like implementing a XOR logical operator. Do you know the XOR operator means you have two Boolean variables, either one is true, not both. Okay, that's the XOR operator. Well, with a perceptron, you cannot model XOR because it is not linearly separable. Okay, whatever line you try to draw, you can't separate the negative examples from the positive examples. That caused the very first AI win. So before this demonstration, this formal proof, the perceptron was the new thing, the hype thing in research. After this, more or less everybody quit doing research in neural networks until somebody else arrived and basically defined more complex architectures that were able to do non-linearly separable examples. So this was a very big hit for research in AI. Okay? Keep in mind that at that time, lots of money were poured into research in AI. And this simple thing actually made the money stop. So that's a really practical implication of having this sort of thing. Anyway, the perceptron can also be used for regression, so not only for binary classification. Simply, you do not use any threshold. Okay? You don't need a threshold because you don't need to tell somebody true or false. You simply give in input the combination of in output the combination of the inputs that you got. In this case, usually, obviously, you use a different loss function, not the sign of the prediction, but you use something like the root mean squared error or the mean squared error or the mean absolute error, whatever. But you can use the perceptron for doing regression. Okay? Keep in mind that the perceptron nowadays is not used in practice, actually, for this reason. If you're not sure whether your predictions, your data points are linearly separable, it is a waste of time to use the perceptron. So basically nowadays the perceptron is dead, is forgotten. Instead, another kind of linear prediction model, keep in mind that with linear prediction model, we don't mean that we are capable of classifying linearly separable samples, okay? No. With linear prediction model, we mean that the prediction model works with a linear combination of the input features. Logistic regression is very famous, very widely used in medicine, in many different application domains. Basically, the intuition is that with logistic regression, you model the probability of the prediction target being 1, so be that specific class. You can work with logistic regression with a binary classification or with a multi-class classification. You model the probability of being, for this data sample, to belong to that class as a probability distribution between 0 and 1. Okay? So if the output for logistic regression is 0.1, it is not likely that this data point belongs to that class. For another class, it could be 0.9. So it is highly probable that this example belongs to that class. And you can iterate this reasoning for every class. So you have a probability distribution over classes. For each example, you have this probability distribution over classes. Usually, obviously, you pick the class with the highest distribution if you want a specific classification. And this is basically the formula, okay? So the probability of the target class being 1 given your evidence. And this is the parameters that you want to learn, okay? This is the shape of the function that you want to learn. Being a probability, the output is always between 0 and 1. And actually, it resembles this function, which is called a sigmoid. Okay? This is the sigmoid function, and these are the parameters. Actually, this is the kind of function you expect. What does it mean? That depending on the features, the x, okay, you are given a probability that lies here, a probability of belonging to a certain class. So here you are in a low probability of belonging to that specific class, higher probability of belonging to that specific class. The shape of the function is simply because it has to be confined between 0 and 1. Okay? You can have, if you want, you can try to do logistic regression, a variant of logistic regression, with a different function. Okay? In fact, we will see that when we will talk about neural networks, this will be called the activation function, and you can have many different shapes. Also here, I put a nice, actually blog post, I think it is this time. But again, it is a nice sort of visual guide to linear models, and in particular logistic regression. And this actually is a, oh sorry, I'm not showing to you, not like this, but like this. Okay. This is actually a nice series of articles. Okay, if you want to take a look, they are quite nice, that actually try to explain in the most visual friendly way possible all of this kind of stuff. So k-nearest neighbor, decision trees, and also things that we will see in the future. Actually, our next batch of slides will be support vector machines and neural network, which are multi-layer perceptions perceptrons at the very core. So here you have this kind of visual explanation. You have a data set about the weather. You have obviously the code to implement this. And you have this kind of explanation about how logistic regression works. So you take a specific sample of the values of all your features. Okay, so whether it is sunny, raining, windy, temperature, humidity, strength of the wind, I don't know. You multiply and add, and then you apply the logistic function. If it's below the half treasure, it's a negative prediction, otherwise it's a positive prediction. This is an example with a binary classification. And again, you have also some sort of visual explanation of how training weights work. Okay, so how actually training our parameters that we called beta, that here I think they are called W, how it works. So that's quite nice. Here you have the predicted probability for, here I think you only have 2 classes for all the samples, and how do you compute the loss, and how do you train. So it's quite well made, okay? So if you want to know all the nuts and bolts, that's a good series of posts. I looked at all of them. I think I linked only this one in the slides, but I looked at all of them. They are quite well made, okay? The sigmoid function actually is not so different from the perceptron, okay? From the sign function that we used in the perceptron. Simply, in the perceptron, the function shape was this one, okay? Based on the sign, if it is negative, you are here. If it is positive, you are here. And if it's 0, you don't really know where you are. With the sigmoid, you have a smooth version of this hard threshold that we had before. So they are very very similar. Okay? Okay, fine. So in logistic regression, we know that we have a different shape of the function. How do we train the coefficient of the function? Because remember that in the sigmoid function, we had some coefficient to estimate, okay, what we call beta. Again, we have a loss function, and a typical approach is to maximize likelihood function, which is called what is called a likelihood function. What is the likelihood function? Well, the core idea is very intuitive. Try to adjust your parameters beta in a way that the output of the logistic function, okay, is close to 1 for the positive examples and close to 0 for the negative examples. So you have your prediction. If the output is close to 0, you predict a negative example. No, it doesn't belong to this class. If your output is close to 1, you predict a positive class. Yes, this data sample belongs to the positive class. That's basically what the logistic regression does. Okay. Obviously, in this case, you are maximizing a likelihood function. If we want a loss to minimize, we just take, for instance, the negative of the likelihood function. How can we interpret the parameters? I mean, decision trees were nice because they were easily interpretable. So let's do a check. Is logistic regression easily interpretable? Well, yes. Because, for instance, if we look at the parameters of any single feature, okay, the parameters are associated to each of the features, humidity, temperature, whatever. If we have a high parameter, a high beta, a high W, weight, coefficient, call it whatever you want, there is a bit of overlap terminology here. If you have a high coefficient, this means that that feature has a strong positive correlation with the positive class. So if the feature is positive, there is a high probability that the predicted class will be positive. Okay? Instead, for instance, if the parameter is near 0, it means that that specific feature is more or less irrelevant. So you could even remove it from the training set and do not lose accuracy in prediction, because it's more or less just noise. Instead, if the parameter of a given feature in your dataset has a low value, okay, it means that if the value of this feature is positive, then the class is negative. So it is an indirect correlation, if you want, okay, between the value of the feature and the prediction. Obviously, we have an example of all of this. This time we are using datasets that you can find on the web. This is a customer churn, so a typical application of machine learning is trying to predict the chance that a customer will terminate the contract. Okay, this is the sort of stuff that all of those services like paid services, paid subscription services like Spotify, Netflix, Sky, whatever kind of subscription service you have, you can bet that they are doing this kind of churn analysis, churn prediction periodically, if not continuously. Okay? So in this case, it was bank customer churn. So the probability that the customer would leave my bank and go into another bank. This is pervasive in the real world, okay? Any sort of company that has a sort of relationship with customer does this. Even supermarkets, if you have a fidelity card, basically, you want to do customer churn prediction. So we have this kind of data set, all of these attributes. The customer ID, for instance, it is unused. Who cares about the ID of a customer? I mean, what can I expect to learn from the ID of a customer? Nothing. The credit score instead, it is, I think this measures how good of a creditor or debitor the client is from a financial standpoint. The country, the gender, the age, that one could argue should maybe be removed to not have a bias. Tenure, I think, is the kind of job, the lifestyle. The balance, how much money it has on the account. The kind of financial products I think the user is subscribed to. The kind of credit card it has, all this kind of stuff, okay? Obviously, there is the target variable, which is the churn. One, if the client has left the bank during some period, 0 otherwise.